Hi, my name is Paul Meeks. I'm the president of Worthington Products located in Canton, Ohio in the United States. And it is my absolute pleasure to be able to address you today over the next 15 minutes. And we're going to talk about the Kamuzu Barrage Project. This is an area in lower Malawi where the hydropower plants would shut down routinely due to massive aquatic weed problems. So we're going to detail over you what the problem was and then also how the problem was solved. So we're going to switch screens here and we're going to go over the project. Thank you so much.
I'd also like to acknowledge the great support that Greg Saunders provided in preparing this paper. Greg is the senior engineer with Revelstoke Design Services located in Winnipeg, Manitoba. I'm going to start with a little perspective so you know where the projects are that we're talking about. Malawi is a small country located in South Central Africa, as you can see on the map. And the Kamuzu Barrage is located in Lwande, which is south of Lake Malawi. And Kamuzu is a control structure above Malawi's primary hydropower plants of Nakula Hydro, Tedzani, and then Kapachira Hydro. And together, those three plants make up roughly 98% of Malawi's hydropower generation, and that is their primary source of power for the country. So these are critical facilities. And here you see a perspective on the Shire River scheme. It consists of the Upper Shire, the Middle, and the Lower Shire, and the primary power plants are located on the Middle Shire River, where essentially there's roughly a 300-meter drop between the Kamuzu Barrage in Lwande and the Kapachira Dam. The problem that hydropower operators face, especially in equatorial countries and just in warmer climates, is the problem of aquatic weeds. Typically, that would be hyacinth. And for Eskom, who is the owner of the power plants in Malawi, it's been particularly problematic for them. For example, in 2001 at the Tedzani complex, aquatic weeds came down, resulting in the intake structures collapsing, and that one event cost over $12 million in damages. In 2005, at the Nakula hydroelectric power plant, it was estimated that they had almost 350 hours lost to load shedding. And during that same year, during another event, the Kapachira power plant was damaged by weeds, and that was another very costly cleanup effort. And also in 2005 at the Tedzani site, the weed infestation that year was so bad that they lost roughly 124 megawatts in power generation. So this is a very serious problem for Eskom, and especially because the country has less power generation capability than what the demand is. So anytime you're shutting down these power plants, it has severe consequences for the country and especially for the economic output of the country. And let's be clear, this is not a problem limited to Malawi. This happens all over the world. This is absolutely a global problem, and the solutions are not that simple. And you see that in these examples here where you have in the upper right corner a beautiful looking boom line. Unfortunately, in the lower right corner, you see what happened once they started getting some debris loading and some water flows at the same time. So it's not an easy solution, but it is a prevalent problem worldwide. How prevalent and how serious is the incident? Well, it happens all the time. Here you're looking at an aerial image of the Nalubali hydropower plant, which is located in Uganda, just off of Lake Victoria. And this is a headline from April of this year, April 14th, when a massive floating island of hyacinth broke free due to higher waters, and it drifted down and it blocked the intakes of the upstream Nalubali hydropower plant. Unfortunately, that caused a cascading effect for the downstream power plants, and the result was a nationwide power outage that lasted about 2 hours. Unfortunately, that power outage occurred just 15 minutes before the president of Uganda was scheduled to address the nation in a nationally televised conference regarding the COVID-19 crisis. Now, you can see in the lower left corner the intake for the hydropower plant, and then you see on the bridge in front of it a lot of excavators. So the national outage lasted 2 hours. This particular hydropower plant was out of commission for 2 weeks. So I can only imagine the cost that incurred to them in removal of all of this debris, in the load shedding, in the power loss, and then not to mention the reputational harm to the company that would occur when you have a nationwide power outage caused by something like this. So how does this look like from the perspective of a power plant owner or operator? Well, here's a diagram that gives us an illustration of what we're talking about. You have aquatic leaves, be they hyacinth, elephant grass, red fern, or water lettuce. And they come downstream, and what they do is they clog your turbine intake screens, and they also block your critical spill gates. That results in a reduction of water levels. And so what you end up getting is reduced energy production. And now a lot of you are operators of hydroelectric power plants, and you're in business to generate power. So this is cutting your revenue. You also have a breakdown of equipment or excessive wear on equipment or even a failure of equipment. For instance, we saw with the Tanzania examples where their intake screens or trash racks had collapsed, but you're also taxing a lot of your trash raking equipment and other type of equipment. So you're putting a lot of wear and tear on that, and that leads to very costly maintenance and repair costs. And ultimately, all of these come together to cause your power plant operators to lose revenue, to have increased costs, and preferably they don't have this, but in many cases, you have to shut your plant down. So these are very serious consequences and very costly consequences. So we're going to take a look at the Kamuzu barrage and what the solution was there. So the barrier at Kamuzu was really part of a much larger project, and the key component of that project was to replace the original 1960s era Kamuzu barrage, which is a bridge with radial gates spanning the Shire River, and they replaced it with 14 new radial gates for a higher design flow, which went up to 1,600 cubic meters per second. But another key feature of the new barrage was they wanted to raise the water level on Lake Malawi. And the reason they want to do that is because they've been suffering from droughts through the past several years, and they were not getting enough water volume on the Shire River for some of the power production needs that they had. So it was absolutely critical that they were also able to raise those water levels to counter the persistent droughts that they had had. Now, the boom itself, and you can see an image of the boom right after it was installed, and we see a weed harvester that they have there. The boom itself was designed for a 1.2 meter exposure above the water line, a 70 centimeter exposure below the water line. It was designed for 1.3 meters per second of surface water velocity and 29.5 meters second wind speed. We didn't factor wave loading in there, and the reason for that is because, as you can see in this picture, once the weeds come down, they're so dense and thick that any waves that might have been generated would have been dampened by all these weeds. So it really wasn't a design factor coming into this particular project. And then what you don't see here is that at the end of this boom line, there is a new weed removal station that has some large cranes that can remove the debris so much more effectively than the weed harvesters that you see here. I think they had an improvement of roughly 300% on the weed removal capability and efficiency here. The aerial image that we're looking at here was taken in 2013, and this shows the original Kamuzu barrage, and then you can see in the middle of the picture, you can see the original boom line, which was just a small 16-inch diameter boom supplied by Worthington Products. You can see that it did hold back some debris, but it needed to be removed and improved because it just wasn't effective enough and sufficient for the heavy loading and the heavy amounts of debris that they do get on the Shire River. So the Shire River debris boom at Kamuzu was done properly, and what I mean by that is that prior to embarking on this project, the client and their engineers focused on the solutions before they focused on a particular type of product. And that would be our advice to anyone out there considering a debris boom project, is that before you say you want X, Y, and Z type of product, you first focus on the solution. You start by working with the boom suppliers and talk to multiple boom suppliers, not just one, and talk with your engineers and your operators so that everyone understands what the problem is and that everyone takes into account the multiple input factors that may affect the performance of the boom. And so by developing a solutions-based approach like that, it involves designing the right solution for that particular problem, and ultimately you're going to achieve the desired goal. So what are we showing here in this picture? This is an example of an HDPE pipe boom. The material itself is excellent. Unfortunately, the client approached in this particular site, the client approached it with the intent of just wanting this type of product. So they didn't really look at the conditions coming into it. So the result, as you can see, was an absolute failure to perform. And I don't necessarily blame the product on this one. This was more of a failed approach to the project. Now, many of you listening right now may be familiar with Worthington Products and one of our barriers, which is called TUFFBOOM. And you can see TUFFBOOM here in the picture. This is actually a photo of the original weed boom in Malawi at the Luandi or the Kamuzu barrage. And you saw a couple slides ago an aerial image of it. And you could see that, yes, it was holding back debris. But this was absolutely not the right solution. And this was supplied back in the early 2000s. And essentially it was just send us a boom line and we'll put it in. And there was no thought going into as to how you angle the boom, what the conditions were, or anything else. It was, we just want this product. Let's try it out and see if it works. And we would say it was only marginally effective here. Without getting into details, and I have the details in my paper, but without getting into the details, the factors that you should be looking at for any debris boom project are river hydraulics, water velocity, wind, waves, ice, debris loads. What is the function of the boom line? Do you want it to stop debris? Do you want it to divert debris through a spill gate? Or in the case of Kamuzu, do you want to divert it to an area where you can remove it? We also need to look at water level changes for countries where there's a lot of silt flushing, such as what we see in India and Ecuador and in China. We need to take a look at the effect of opening radial gates very close to the boom line. So we want to take those factors into consideration. We need to look at anchoring. And there's a whole number of factors that really need to be looked at before any successful debris barrier project should be embarked upon. And here you see an example of a debris project in the country of Laos at the Xayaburi hydropower plant. And you can see it's working very effectively. And this debris boom in particular is designed to deflect debris through spill gates so they can flush it on downstream. For very critical sites and for sites where you may be trying a new design or something, you should also consider, and your barrier supplier and or engineer should have this capability to be able to do flow modeling so that you can see where the water is going to flow, but also where the debris is going to flow, what the reaction of the boom line will be under different flow conditions, to see what the loads are on the boom, and also to see if that boom line is going to remain upright or if it's going to flip or roll. And so flow modeling, and we in our case use a software program called Flow 3D, which is excellent. Flow modeling enables you to essentially test the barrier before you put it in. Now, for a number of sites, we also will do a structural analysis, and here you see an image on the right of one of the structural analysis that we did for the log booms or the debris boom at Kamuzu, because it is such a critical location. So we felt that flow modeling and structural modeling was going to be appropriate at this site. We also relied on our engineers, but we wanted to verify what we were seeing with the engineering and the flow modeling and everything else. So when we were a long way through on the production of the units, at least the initial units, we went to a quarry in Portugal and we assembled a number of units just to see how they floated in the water, if the flotation matched what our modeling was showing, and also to get an idea as to how these things would assemble and to determine if there's any easier ways we can make it for the client when they have this thing and they have to put it together and put it in the water. So here you're seeing an example of the initial float trials that were conducted in Portugal for the Kamuzu Barrage project. And here you can see at the culmination of the project, an aerial image. In the lower center portion of the screen, you see the new Kamuzu Barrage. It's a fantastic looking project. You see in the center of the screen the original debris boom that we showed some photos of earlier. And then in the upper section of the screen, you see the new boom line. Notice the boom line was installed at a very sharp angle because we wanted to direct all of the debris down into the debris removal section where they had these large cranes to remove it. You can see in here a weed harvester still operating in here to try and collect additional debris. And then you can see a large field of water hyacinth. And this field measures roughly 350 meters long by 150 meters wide. So as you can see, it's a very, very effective barrier. And the reason for that is because we went through the steps to define the problem ahead of time before we presented the product or the solution. And that is the one thing we want to have everyone just carefully think about, that let's not approach these projects from a product base, but from a solution basis. And then here's just another view of the completed project showing the assembled units, the large angle, a fairly decent field of debris behind it, and a very happy client in this case. So to summarize the Kamuzu project, if you have the proper advanced planning for these projects, you are going to achieve your goals. And in the case of a power operator or power generator, we assume those goals are that you want to be able to maintain the reliability of your plant and equipment. You want to be able to maximize the life of your equipment, minimize your costs. Obviously, you want to generate revenue and you want to control your maintenance costs. And what it gets down to is you want to be able to generate power on demand. And by putting in an effective debris control, debris stopping solution, you will achieve all of those goals. So thank you for allowing us to present this paper. Again, my name is Paul Meeks. I'm with Worthington Products, and you see if you wish to contact me, my email address. Also, the QR code you're seeing in front of you, if you scan